OK. Bonjour tout le monde. Merci d'être venu. Welcome. Thank you for coming. So this is week 9. And I hope to finish the electron gas today, but there's still a lot of stuff I'm not sure. And then we will start to discuss density functional theory, just to set up the what is the sort of the foundation of much of solid state physics. And then we will go with the Hubbard model and the week 10 dynamical mean field theory. So are there any questions? The last time I told you there would be problems with the Hartree Fock approximation. So we will think a little bit more about the Hartree Fock approximation, and I will show you the pathologies of that approach. And I will show you then how to get rid of this pathology. And it will be in the end, what we will want to have is the screened interaction instead of the bare interaction. It's just as simple as that. And I will simplify a little bit the expressions and show you how we get the Fermi liquid result, which is that at low frequency, the imaginary part of the self-energy goes like omega squared plus t squared. And we will end, hopefully if we get there, we finish the discussion of the electron gas. So one thing I want to say is that you see, if we go back to this for the density correlation function, if we were to just do perturbation theory in powers of the interaction, what would happen? We would get that the susceptibility is the bare susceptibility minus V minus, let me put it differently, minus chi0 VQ chi0 plus chi0 VQ chi0 VQ chi0, which as you can see is a real disaster, huh? Because this goes like 1 over q squared. So chi would just be divergent at low frequency, like 1 over q squared, and then like 1 over q4, and like everything. So if you think in terms of simple perturbation theory in the Feynman way, then you see that you get this sort of paradox. But this should be compared with what happened with the Green's function. You know, the Green's function G was also G0 plus G0 sigma G plus G0 sigma G0, whoops, G0 sigma G0 plus etc. So it was less obvious in this case, but that's also problematic here. But with this formalism, we see here that what we have really is a self-consistent equation for this susceptibility, and this here acts like a self-energy, just like in the case of the Green's function. In other words, this I can write as G is equal to G0 plus G0 sigma times G. And then I can invert this equation, and that gives that G minus 1 is equal to G0 minus 1 minus sigma. And you just need to put the sigma on the left and then to realize that if you multiply by G0 minus 1, so you get rid of this G0 minus 1, and on the right hand side you get 1, so this is G minus 1. And in the same way here, what we have with the susceptibility is that the chi is equal to chi 0 minus, whoops, I see chi and I write G. Bad start. This is a chi 0 minus chi 0 V chi, right? The chi comes in both places. So this means that chi minus 1 is equal to chi 0 minus 1 minus plus, in this case, VQ. So you see that this little piece here that became V of Q acts like a self-energy for the response function, the susceptibility. Okay, and it comes in very naturally in this formalism. If you just go perturbation theory straight, it's nonsense. And then you ask, why should I resum to infinity? Well, you should resum to infinity because the real equations are this. Okay, they're self-consistent. So that's a little point I wanted to make, a point of principle. And that shows the power of this Schwinger approach, where you get this directly without having to argue, well, we should resum, and it will make the result finite. And then you ask, why should you resum an infinite sum of divergent terms and get something finite? Why should I trust it? Well, in reality, what you're doing is just solving a self-consistent equation. And we saw for the susceptibility that it comes out naturally if you look at the Thomas Fermi at screening, for example, using either the self-consistent potential or the external potential. And the relation we got between chi, this relation we got directly from this sort of simple-minded thinking about dielectric functions. Okay. Okay. So much for this little remark. Okay. So let's go back to this. And before I discuss the pathologies, let me remind you that here what we had was a Green's function. And we had to sum, here we had to sum over K prime. So we had to sum over these Matsubara frequencies, but that just gave a Fermi function. Similarly, for calculating the density, we needed to sum over Matsubara frequencies. And that gave us the Fermi function, which at 0 temperature is just a step function. And because the density here has not changed, it means that the Fermi wave vector has not changed. And so what happens then is that the chemical potential is renormalized. Okay, now there's another way to think about this, which you will say, well, this is ridiculous, but you will see that it will be very helpful when I discuss broken symmetries. You see another way to look exactly at this thing is to say that, okay, the Hamiltonian I will write like a trial unperturbed Hamiltonian plus H0 minus H trial plus the interaction. Okay, so in this, the Hartree Fock approximation can also be seen in a variational point of view. That's discussed in the notes, but we don't have time to look at this. So here we say, okay, I start with the trial Hamiltonian. So what will happen here? What will happen is simply that instead of having, and I do perturbation theory in this trial Hamiltonian. So here what I will have is f of epsilon tilde of k minus mu. So epsilon, no, yeah, let's just say it's just a question of notation. Let's just say epsilon tilde of k. So in other words, what I tried for H0 tilde is just sum over k, sum over spins of some trial epsilon tilde of k, c dagger k sigma, ck sigma. Okay? So the unperturbed Green's function is just involves this. So when I do the sum over Matsubara, see, this is replaced by epsilon tilde of k. And when I do the sum over Matsubara frequencies, I get this. Okay, then the question arises, well, how do you determine this epsilon tilde of k? Well, this epsilon tilde of k you determined in such a way that the the self energy is 0 at the Hartree Fock level. Okay, because now what will be the self energy at the Hartree Fock level? You see, the Hartree Fock energy will be the sigma will have now a one-body term, which will be epsilon k minus epsilon tilde k, right? Which is this piece, and then it will have the usual result. In other words, this minus this. Okay, and now if I ask that this self energy is equal to 0, what do I get? I get that epsilon tilde of k is equal to epsilon tilde of k is equal to, so epsilon k minus sigma 1 of k. Okay, if I put the chemical potential, I have plus mu. Okay, so this is sort of trivial at this level. But when you will see that when we break symmetries, we will try Hamiltonians here that break symmetries. H0 will break symmetries. And then we will ask that the self-energy at this level is equal to 0. And we will be able to formulate dynamical mean field theory that way also. Okay, so this is just this is called renormalized perturbation theory. So instead of doing perturbation theory around the bare epsilon, the bare Hamiltonian, we do perturbation theory around some other Hamiltonian that we determine self-consistently. So in other words, another way to look at that is like it's sort of an effective medium theory. So you say that, okay, I'm going to look at the best epsilon tilde of k that looks like a free electron and that leads to 0 self-energy at the Hartree Fock level. Okay, so up to now I've done nothing but just reformulate exactly what we had here in this way. Okay, are there any questions? Is that mysterious or? Okay.
So that can only apply if the self-energy has no frequency dependence.
What? I'm sorry?
That can only apply when the self-energy has no...
exactly. That's a very good comment.
Dependence.
Very good comment. And when the self-energy has a frequency dependence, and that will be dynamical mean field theory, then we will have to postulate, we cannot have a non-interacting Hamiltonian we need to have a non-interacting Green's function. So, so in other words, that will be a more general point of view. And the best way to see it when we get to this case, when we have an effective mean field that is frequency dependent, is to look at an action formalism, which is like moving from Hamiltonian to Lagrangian formulation. But I think we will be able to stick with this, and it will still look okay. But it's more natural to do it in this with this Lagrangian, this action formalism, which maybe I will have time to look at. Maybe I won't. Okay. Very good remark. And when we do ordinary mean field theory instead of dynamical mean field, yeah, that's basically what happens, is that the mean field is always static and frequency independent. Okay. So now I just want to evaluate this thing here and show you that there are problems. And the problem is that the effective mass is 0. So you remember that I can replace this by, at 0 temperature, by theta of k minus kf minus k. Okay. So how do we do this this integral? I have minus 1 over 8 pi cube. The sum over Matsubara has been done. I should have, sorry, this was the wrong equation here. And it has stayed for 2 days, which is really a bad sign on me. I didn't see it. Okay, you understand? We had done the sum over Matsubara frequencies. That's why we had a Fermi function. So 1 over 8 pi cubed, then I get 0 to k Fermi of k prime square dk prime, and then I have the integral. I go to polar coordinates, and I have 2 pi for the azimuthal angle, because nothing depends on the azimuthal angle, just the cosine between these two vectors. So I have 2 pi d cosine theta from -1 to 1. And this is e squared over 4 pi epsilon 0.
What is this 8 factor in front of 8 pi cube?
Thank you.
Oh, yeah, okay.
It's a parenthesis error, which causes me huge problems in programming sometimes. When you put okay. So e squared over 4 pi epsilon 0. And then this is just 1 over k square plus k prime square minus 2k k prime cosine theta. Okay, this goes with this. So you see the integral over cosine theta is easy to do. This is a log. And because we have said that there's nothing at q equals 0, so when k minus k prime equals 0, this is cancelled by the background. So I can take the principal value integral. And now the principal value of integral, so the integral dx of 1 over x minus x prime, principal value. Please do it for yourself. I mean, you can always go infinitesimally close to the pole here at x prime, and then do the other integral and so on, and you will see that the integral is the log of the absolute value of the argument. So this is easy to do. So this gives minus 1 over 4 pi square times e square 1 over 4 pi epsilon 0. And then I get the integral 0 to kf of k prime square dk prime, and then I get 2 minus 2 kk prime, and I get the log of the absolute value of k minus k prime square divided by k plus k prime square. And this is not the absolute value, this is just a parenthesis. So this is evaluated at cosine theta equals +1 and at cosine theta equals -1. And this is just the, because when, it's the usual thing, when I differentiate this, I will get 2k minus k prime, and so I need to get rid of it this way. Okay, so there's 1k prime that goes away, and then this is just some integral you need to do. Okay. So I tried to memorize the answer, because I think it's not very useful to spend a lot of time doing this. This can be looked up in tables or on the with algebra, software, Mathematica, or whatever. So the final answer is that sigma is sigma 1 of k is equal to minus e square over 4 pi epsilon 0 kf times 1 plus 1 minus 2 y square over y times the log of the absolute value of 1 plus y divided by 1 minus y. Where y so I'm sort of working upwards now, where y is equal to k over kf. Okay, now where is the problem with this? The problem is when I compute, well, first, before I talk about problems, let's see that it is, it's nice. There's an aspect of this which is nice. If I compute, if I look at so sigma 1 divided by the kinetic energy, which is kf square over 2m, then I get that this is m e square over 4 pi epsilon 0. There are constants that are missing, divided by kf. So this is 1 over kf a0, which is rs. Okay, we said it was an expansion in powers of rs. Okay, so this part is nice. But now when we want to compute the effective mass, there we run into problems. The effective mass, m over m star, we said is equal to 1 plus d sigma d zeta k divided by 1 minus d sigma d omega. But here there's no frequency dependence, right? So this is just 1 plus d sigma dk d zeta k. Okay, so now if we take this expression and we differentiate with respect to k, is like differentiating with respect to y. And the problem comes from this this log here. So if I differentiate this with respect to y, you say I want to evaluate the effective mass at the Fermi wave vector, so at y equals 1. Okay? So clearly the log here at 1 plus y will not cause any problem, but the log of 1 minus y will lead us into problems. So if I focus just on this piece, d dy of 1 over y minus 2y times the log of 1 minus y. Okay, the piece that will cause, so the differentiating the log with respect to y will not give any problem. I will get 1 over 1 minus y in the denominator. But here, what I have do I get this 2? Is this 2 correct? I think I have a mistake.
In the note, the 2
What?
is in the note. The 2 is at the bottom y.
Yes, okay. Okay, thank you. You saved me. Yes. So 2y, 2. Okay, so the point is that 1 minus y squared is equal to 1 minus y times 1 plus y, okay? So when I differentiate the log, I get another 1 minus y here, and that's no problem. But when I differentiate this, and I evaluate at y equals 1, the prefactor is not a problem. I mean, so when I differentiate, it will give you 1 minus 1 over 2y squared minus 1 over 2. And then I have the log of 1 minus y. So when y equals 1, this is finite, but this goes to minus infinity, or to plus, yes. Okay. So it means that here I have 1 over m star, so it means that m star goes to 0. Okay. So this is the problem I have. How do we solve that problem? Well, it's a little bit like what I said at the beginning, that you really need to sum things up to infinity. So look at the expression for sigma. It involves this thing here, which is just like the charge fluctuations. And we know how to compute the charge fluctuations. So we might as well take that into account. So we saw that when we derived the equation of motion, we saw that the sigma of 1 bar times g of 1 bar 2 is equal to minus v of 1 minus 2 bar times psi dagger 2 bar plus psi 2 bar psi 1 psi dagger 2. So where did that come from? Well, when we differentiate with respect to when we look at the equations of motion for psi 1, when we commute with the interacting part of the Hamiltonian, we get rid of psi dagger 1. So we're left with psi 1 here, and we're left with 3 operators. But then the G has a psi dagger 2 appended to it. So that's where that comes from. That's where that came from. Now you see that if I look at 1 plus here, in other words, this is like the trace. You see, if I put a bar, this is like a trace here. Then this becomes 1 plus. And if it becomes 1 plus, it means that I want to add it this, I want to add it on the other side. So I have psi dagger 1 plus psi 1, and I get rid of the minus sign. And you see that this sigma g is really related to potential energy. 1 minus 2 bar. And another way to say it, it's related to charge fluctuations. So, so let's go back to this and see what happens. So this term is 0. So I get this term. I get the minus this. And I get minus. And now I will write everything. So here I will have K plus Q. And this in our calculation of the charge fluctuation was just V of Q, right? So I have some V of Q that's going here. And I have this K prime and K prime plus Q, and I have V of Q here. Okay, and this, what is this? This piece here is just this plus this plus this. Okay, this is the sum over all these diagrams. And I have an extra line here, okay? So this is sigma. If I look at sigma g, you see what would happen for sigma g is that I would multiply by g here. And then I would get just another bubble, so that doesn't change anything. And then I have some V of Q that connects these two. Okay, which is like the potential energy. So we will see all of this algebraically now. Do you have any questions? And you will see that the final result is just really replacing the bare Coulomb interaction by the screen Coulomb interaction. So as usual, at large frequency, the Coulomb interaction is not screened because the dielectric constant goes to epsilon 0. But it's very important at low frequencies. So high frequencies is like the plasma frequency, so it's several electron volts. We're looking at phenomena that occur at much smaller energies. So in particular, omega goes to 0. So it's important to screen the interaction. So it means that I have that sigma now of K And now for K, let me write, I think this will save me some time here. So by K, I mean K vector and IKN, okay? So sigma of K is equal to, so this term, so that's minus sum over I so here I will put Q here and K prime here. So I should put K prime, well, yeah, K double prime, not to mix with this one. But okay, so sum over IKN times temperature times the integral K prime d cube K prime over 2 pi cube, and then I get V of Q times here I will write 1 and you will see why. So I write 1 and I have a plus, okay, the minus sign is common to both. One of the V of Q's there. So now I have a V of Q times chi N of Q, and I have G of K plus Q, okay? So G and the K prime. So G of K prime plus Q, then this piece is just the susceptibility. Now this is some of the bubbles. And I have the V of Q, and this by itself is not the susceptibility, it's minus the susceptibility. So I have a minus sign here. And yes.
Just a question about that. For the first term, why do you have a G of chi prime plus Q when you have written G of chi prime on the diagram?
Okay, because there's an error here.
All right.
Let's see. No, I have to be careful. It's really K plus Q. So what's happening here?
I mean, in the notes you have G of K plus Q, but
here it's K plus Q in the notes?
Yes.
Okay. So let's write it clearly. Here it has to be K plus Q. And here also. Because why? Because I'm coming in with the K, okay? And leaving with K. And I have this Q that's going here like, so it's really K plus Q. Thank you. Okay. And so here what I should do, that's the origin of my mistake. I should integrate over Q. It's just a bad day. Okay, that makes more sense. Everybody agrees with that? So I have to integrate over Q here. I have to integrate over Q. And now everybody's happy. Okay, I don't know. I disconnected, sorry. So what is this? Chi and N is chi 0 over 1 plus V of Q chi 0 and N. Okay? So when I work with this, you see that what I get here, when I put this on the same denominator, you see that this guy here will become 1 over 1 plus V of Q chi 0 and N. And what is this? This is epsilon 0 divided by epsilon longitudinal of Q. And now we have, I will put, just to make sure that we agree with everything, I will put the IQ one. Okay, so now we have, you see we have the screen Coulomb interaction. Okay, the epsilon here, 0 here will cancel the epsilon 0 in the V of Q. And we have a screen dielectric constant, which is this guy here. Okay. And that will solve all our problems. Okay, so we look at we solved it. We got this right. Okay, so if we look, I will share share my screen. And you see that this is the result of calculations that I will work a little bit through these calculations, but not everything. It's too much. So what is this? This is the self-energy in units of the plasma frequency. And on the horizontal axis is the frequency in units of the plasma frequency, okay? And the dark part here is the imaginary part of sigma. And this line here is the real part. So first thing you note is that the slope is negative. And you remember that's what we wanted, to have a negative slope to have quasi-particles. So that's something nice. The other thing we notice is that okay, this picture here is at the Fermi wave vector. This is below the Fermi surface, and this is above the Fermi surface. So what we notice is that whether we are below, above, or anywhere on the Fermi surface, that's zero temperature calculations. At zero frequency, the imaginary part of sigma vanishes. That's something that's characteristic of Fermi liquids. Now, this straight line is omega minus epsilon k plus mu. So the intersection of this line with the real part of sigma is the place where we would have a quasi-particle pole. And this is also a quasi-particle, and this is a quasi-particle. Now you see there are some other things that happen here where we also have a negative slope and an intersection as well. So if you look at the spectral weight, it's now much more complicated, you see. So there's a delta at the Fermi wave vector, at zero frequency, there's a delta function whose weight is 0.6. And I think this is for RS equals 5, but I have to check in the original literature. I don't remember exactly. And these peaks are related to plasma resonances. So this is when you see the threshold here is when you hit omega equals omega p. And the threshold is different if you're above or below the Fermi surface. And you saw that this other crossing here gave another pole here that's below the band edge. Is more like a bound state. Okay. So this is the result of the calculation, but let me move you through some of the steps. Let's see here, you see, before I erase this, You see that, suppose I have rewritten this V of Q times 1/1 plus V of Q chi 0, okay? Now you see that if I multiply this by G of K, and I integrate over K, in other words, I take the trace like here, but in momentum space instead of real space. What will happen? If I multiply this by G of K, and this by G of K, you see that G of K times G of K plus Q is this bubble. It's chi 0. Okay. So I will get V of Q times chi 0 over 1 plus V of Q chi 0, which is just the dressed susceptibility. So it will have exactly this structure, right? It will have this will become this. I will have a chi 0 here. So this whole thing here is the susceptibility, and that susceptibility is this set of bubbles, and it's multiplied by V of Q, which is this external line here. Okay. So I'm not doing this explicitly, but I just want to show that that it works out. Okay, now I want to simplify this this expression a little bit, and that's what will give us the Fermi liquid result. Okay, my aim then is to find the frequency dependence of the imaginary part and show that it goes like omega square plus pi t square. So I will focus on the frequency dependent part of the expression here. You have seen that the Hartree Fock piece is not frequency dependent. So we will drop. We will just focus on this this piece here. So we will have that the sigma of k will be equal to, now the minus sign disappears, and we get t times the sum over qn, iqn, of integral d cube q over 2 pi cube times v of q times the susceptibility chi n of q times v of q again, because I have v of q squared, so I write it this way. And now I have g of k plus q. Okay. Now let me write, what I will do is I will just do the sum over Matsubara frequencies. So to do that, I will proceed like this. So this is t times sum over iqn times the integral e cube q over 2 pi cube. And now I will use the spectral representation for this guy. So this means that I can write a sum d omega prime over pi of v of q times chi double prime and n of q and omega prime times v of q, and here this is divided by iqn, omega prime minus iqn. You see that the integral d omega prime of chi double prime divided by this, that's the spectral representation for this. And now the Green's function is just the bare Green's function, so it's equal to 1 over ikn plus iqn minus zeta. Zeta means that I include the chemical potential. Zeta of K plus Q. Okay, so that's a very common trick that allows you to do the Matsubara frequency sums, to use the spectral representation. Because now you see this is a form that we know how to handle. So I will just finish with this, and we will have to do Fermi liquids next time. I'm really sorry for this stupid mistake of integrating over K prime. It's really a bad idea. Somehow my brain disconnected this morning. Okay. So how do we do this sum over IKM? Well, we write T times the sum over IQN. I put a minus sign here, and here I write 1 over IQN minus omega prime. Okay, so I just use the minus sign here. And then I will use this partial fraction decomposition that we are used to. This is IKN plus IQN minus zeta K plus Q. And here I get 1. Okay, now put this back as in a common denominator. You see that what happened is that I get IKN. I get what happened there? Yes.
In the note, it seems to be the same way, so I guess it's fine.
No, but I'm still running into problems. So it's fine, you say, from the notes?
Well, it looks fine.
Yes, it is. It is.
So here I have, okay, yes, okay. I reconnected. So IKN plus minus zeta K plus Q. Okay, the IQN drops out. So I want to do the sum over IQN. So that's fine. So minus zeta of K plus Q. Okay. Now
And you forgot omega prime.
The sum over Matsubara frequencies. Then this becomes a Bose function of omega prime. And here I have minus, it becomes plus. Here you see, even though I sum over IQN, which is a bosonic frequency, it's added to a fermionic frequency. So even plus odd is odd, right? So this is really like summing over odd Matsubara frequency. So that gives plus Fermi function of zeta K plus Q. And here I'm left with 1 over IKN minus zeta K plus Q.
You just forgot the plus omega prime.
And I forgot omega prime here. So IKN, this becomes a plus omega prime. Thank you. Okay, I have everything right now. Okay, so now you see I can get rid of this sum over Matsubara frequencies. And I still have the integral over omega prime. I get rid of this. I get rid of this. And I can replace by this. Now you see what I will do is now I can do the analytic continuation on the frequency of this guy. I can replace this by omega plus I eta. And it's important that I have done this sum over Matsubara frequency before doing the analytic continuation. You see? If I had done the analytic continuation, that's the usual rule. It's not the first time I say this. If I had done the analytic continuation here, then I would have a real problem because when I sum over IQN, then this would be real, and this will be a Bose function, but it should be a Fermi function. So the mistake you do by analytic continuing before doing all the Matsubara frequency sums is that you analytically continue through a lot of poles along the imaginary axis, and you shouldn't do that. Now I don't have any poles in the way, so I can do the replacement. So, and we will start from here because it's already time to stop. But I get here I get times n Bose of omega prime plus Fermi function of zeta k plus q divided by omega plus I eta minus zeta k plus q plus omega prime. Now I cannot resist here to go one step further, which is to say that what we want is the imaginary part here. So I look at the retarded Green's function, and I look at the imaginary part. So the imaginary part will be what? Will be sigma double prime of k and omega will be equal to, now if I look at this becomes minus I pi times the delta function, right? You agree? Okay. This becomes minus I pi times the delta function. So look at that. I can do the integral over omega prime now. Okay. So the pi will cancel the pi that I get from here. So I'm just left with the overall minus sign. Fortunately, the imaginary part should be negative, so that's a victory. And then I get delta of zeta k plus q and omega plus omega prime. So I can just do, when I do the omega prime integral, I can replace zeta k plus q by omega plus omega prime. You see, this is a proof by erasing. Sorry. Okay. So I get omega plus omega prime. And now what happens when omega is equal to 0? When omega equals 0, at 0 temperature, this is 0. Why? Because if I look at the function of omega prime, the Fermi function is 1 here and it's a 0 there. And this function here is minus 1 here and it's 0 on the other side. So it's 0 everywhere. Okay, so whatever the value of k, I get 0 for the imaginary part at 0 temperature at omega equals 0. Okay, so that's one thing I can show. Because you see this Bose function and Bose of omega prime is 1 over exponential of beta omega prime minus 1, which means that when omega prime is negative, then this is minus 1. And when omega prime is positive, beta goes to infinity, so that's 0. Okay? So that's why I get this. And you see what will happen in the case where I have omega plus omega prime, then the function, this function here will become zero earlier. So I will have a window here of with omega where this will be different from zero. And there's something wrong happened. Something happened here. There's something wrong.
I mean, you just erased the omega prime integral, and omega prime is still there, so that's weird.
Yes, that's weird. Yes, exactly. But I needed to get rid of it to get rid of the delta function.
Yes, so you should replace omega prime by zeta k plus q minus omega, if you want to do that.
No, here I have zeta k plus q, right?
Yes.
So what happened?
I think you need to keep the delta function if you want to have the dependence in omega in those function. If you do the integral, all the frequency will become the zeta k.
Sorry, I cannot hear you. Can you repeat?
Okay, so I think you need to keep the delta function if you want to have the explicit frequency dependence. And if you do the delta function, then you lose all the omega, and you will only keep the zeta k plus q.
Doing the integral over omega prime will replace every omega prime with omega and
let me look at my notes. This is embarrassing. Okay.